Hi everyone. So in the previous video, we went over the idea of global maximum. So in this video, we will look at global minimum. Okay. So remember I told you that the global maximum is the point where the function attains its highest value. A global minimum is a point where the function attains its least possible value. And so another formal way of saying this is if you have a local minimum point x star y star, and the function has this particular point has the additional property that the y star that you obtain at the particular critical point is actually the lowest value of the function, then this particular point is actually the global minimum. We call it the global minimum or the absolute minimum. Now, so there may be points where so the function actually attains its lowest possible value in more than one x value, and you'll see a few examples of how it can be possible. But the broad idea is that a global minimum will be the point where the function attains its least possible value. Now, how do we go ahead and find the global minimum? This is going to be in a way that is very similar to how we find the global maximum points. So first, you start off by finding the local minimum points, which is the usual way of getting the critical points and looking at the second derivative, as the case may be, and classifying if it's a local minimum or not. If there is going to be a global minimum in that function, you can find that by comparing the y values that are so obtained in each of these local minimum points. The particular point which gives you the lowest value of the function, lowest y, will become a global minimum point. But is that enough? Is it enough if you just look at all the local minimum points? That is actually not enough, because the only true way to find if a global minimum exists is to actually sketch the curve and try and understand how the function behaves, how y behaves as we move either to as x approaches either as x approaches plus infinity or as x approaches minus infinity. So we just have to sketch the curve and understand the behavior of the function. So these are the systematic steps that one will take to find the global minimum. Let us look at a couple of examples to see how to go about this. Remember that a particular critical point need not be a global minimum point, because a global minimum point by definition is the point where the function attains its lowest value. So we'll see a couple of examples where a local minima is not necessarily a global minimum. And we saw corresponding examples in the global maximum case. So let's look at examples in the global minimum case. So the first function here, y is equal to 2x cubed minus 3x squared minus 12x plus 9. This was one we saw in the global maximum video as well. So we have two critical points, minus 1, 16 and 2, minus 11. And from the figure here, you can see that 2, minus 11 is a local minimum. Is it the global minimum point? Well, we have access to that particular function. So let's go ahead and graph it and see what that looks like. So let's move to this. So let's graph this function, 2x cubed minus 3x squared minus 12x plus 9. Well, we see that the function does have a minimum at that particular point, 2, minus 11. But is that the point where the function attains its lowest possible value? Well, it doesn't seem to be the case, right? Because for negative values of x, you see how the function is actually taking on lower and lower values of y. So you have a particular point here, say, minus, let me look at a number there. So if we have, say, minus 3, then the function is actually taking on something like minus 36 or something. Minus 36 is much lower than minus 11. So, and we can't pinpoint and say that the function has a single global minimum, because if you move for negative values of x, the function is actually taking on lower and lower values of y. So the function actually does not have a global minimum. in this particular case. Because you can't pinpoint a single value and say that's the lowest value. And similarly, we saw in the maximum video that this particular function actually doesn't have a global maximum as well, because the function is just continuing to increase. Because for the different values of x that you take on, you're ending up finding y values that are much higher than the y value that you found at the maximum. So that's one example. Let's see another example, which is this function, y is equal to x power 4 minus 4x cubed plus 5. Now, when you solve for the critical points, you actually end up finding 2 points, 0, 5 and 3, minus 20. Now, 0, 5 is actually an inflection point. So 0, 5 is an inflection point. And 3, minus 22 is a local minimum. So how do we go about characterizing whether this point is the global minimum? Well, from the general graph of the function, looks like the function just has this one single track and it continues to keep going past this. Now, let's actually go ahead and plot out this function in decimals and see what's happening there. So let me share this. Okay, so the function we're looking at is actually x power 4 minus 4x cubed plus 5, which is this interesting looking function. Let me zoom in a little bit to see whether we have our critical points right. So that's 0, 5, and that definitely looks to be a point of inflection. And we have another critical point here, 3, minus 22, which definitely looks to be the minimum point. Now let's take a bird's eye view of this function. Does the function appear to have a minimum that is lesser than this? Well, it doesn't look like the function is actually hitting on to a point than that, right? Because for positive values of x, the function has positive values of y, which are pretty large, and the same story for negative values of x as well. So the function doesn't actually seem to kind of reduce beyond this point 3, minus 22. So therefore, in this particular example, 3, minus 22 is also a global field. So that's broadly the distinction between local and global maxima and minima. I say maxima and minima because that's the plural for maximum and minimum, and you can have more than one maximum and minimum points in a particular function. So I want you to be familiar with this terminology of local and global optimum points. But don't worry too much about it, because in economics, the functions that we deal with are most likely going to have a peak or a clear bottom. So it's going to be possible for us to pinpoint exactly what the maximum point is or what the minimum point is. So think of, an inverted U-shaped profit function or a proper U-shaped cost function and things like that. So oftentimes, just looking at local maxima is enough to suit our purposes. But it's important to be familiar with the terminology for local and global optimal points. And I hope this video achieves that purpose. So I will stop this video here and I will see you in the subsequent video.